Okay, so probably today is the last lecture. So we are going to do Laplace transform and its applications. I started this topic in the last class, and towards the end we are going to look at two special functions, beta and gamma functions. And see, normally functions that satisfy differential equations are known as transcendental functions. Okay, so there is a open problem also here that beta and gamma functions, we still do not know what differential equation they satisfy, although they are transcendental functions kind of thing. So it's something really interesting for you to look at. In the case of Laplace transform, as I mentioned, so I am going to show you one application for how do you solve differential equation using Laplace transform, and how do you solve partial differential equation using Laplace transform, right? So as I mentioned, for engineering students, they use sort of a table for given a function, look at the Laplace transform. So from T domain to S domain, okay, function is defined in T, and then the Laplace transform is in S domain, right? Some capital F of S kind of thing. Okay, so small f of t goes to capital F of S, right? That's the Laplace transform of function, 0 to infinity e raised to power minus st ft dt, right? That's the formula. Now, so that table, so going from T domain to S domain and coming back from S domain to T domain, the inverse Laplace transform. So those tables are used heavily in calculations. So normally when you do compute some formulas, you will you memorize it and directly use while doing the calculations. Okay, so I think I have done some for some functions I have computed Laplace transform. So let us go to that slide. Yeah, so Laplace transformation of ft is capital F of S, and inverse Laplace transformation of capital F of S is, ये मैं गलत लिखता हूँ तुम लोग बताते भी नहीं हो, right? Should be ft anyway. And so it's linear. Laplace transformation of e raised to power at is 1 over s minus a. Laplace transformation of 1 is 1 over s. So that means inverse Laplace transformation of 1 by s is 1. Laplace transformation of t is 1 over s square. Sine hyperbolic t is omega divided by s square minus w square. Laplace transformation of cos at is s divided by s square plus a square. Similarly, you can find Laplace transformation of sine at and so on, right? For different functions you can find. Laplace transformation exists for only those functions which are exponential order alpha, right, and piecewise continuous, right? That condition I told you. Okay, so we were looking at Laplace transformation of derivative. Why do we need this? Because actually we can use this to transform differential equations from T domain to S domain, and then it will become easy. So Laplace transformation of f dash of t is s times Laplace transformation of ft minus f of 0, or in other words s of capital F of s minus f of 0, right? And the proof was fairly straightforward calculations, integration by parts, right? You can do that. So once we have this result with us, we can actually generalize this from first order derivative to bit further, which is the following: Laplace transformation of nth order derivative of t, and this is s raised to power n times Laplace transformation of f of t minus s raised to power n minus 1 times f of 0, okay, minus dot 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 s raised to power n minus 2 f dash of 0 dot 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 finally minus n minus 1th derivative of 0. That is how the general formula looks like. You can compute, right? Just apply the transformation, right, and then you can compute this value, right? So let us solve an example. Let us do an example now. how do we solve a differential equation? Y double dash plus 4y is equal to 0, y0 is equal to 1, and y dash of 0 is equal to 6. So this is IVP, initial value problem, right? So at the initial point t is equal to 0, we know the values. Y of 0 is 1 and y dash of 0 is 6, initial value problem. I want to solve it using Laplace transform method. So take the Laplace transformation on both sides. Is equal to Laplace transformation of 0. By the way, what is the Laplace transformation of 0? 0, straightforward thing. And here it is a linear, so it will be, Laplace transformation of y double prime plus 4 times Laplace transformation of y is equal to 0, right? Straightforward calculation, because Laplace satisfies the linearity condition, right? So we can do that. Now this is nothing but by the formula s square y of s minus s times y of 0 minus y dash of 0 plus 4 times y of s. So this capital Y of s, remember this is small y, right, is equal to 0. Okay. Now we know the initial condition y of 0 and y dash of 0, so I can substitute here. So essentially I am going to get s square plus 4 times y of s is equal to s plus 6, right? So remember, small y of t. So basically what is happening here, we have a small y of t which goes towards capital Y of s, right? Laplace transform, after Laplace transformation, right? So equation was given, I have taken Laplace transformation, I got this. Now y0 and y dash of 0 I know, condition is given. So I can solve for capital Y of s, which is this quantity, right? So capital Y of s is s plus 6 divided by s square plus 4. So now once we are able to find capital Y of s, I can do the inverse to get y of t, right? So that is a bit straightforward thing, but let me show you how to do it. So this implies that we have capital Y of s is equal to s plus 6 divided by s square plus 4. So now you remember s divided by s square plus 4 is what? You can see if you go here, you see s divided by s square plus a square is of cos of 80, right? So I can use those kind of formulas here to compute. So this is nothing but, so basically I can say that y of t is equal to inverse Laplace, y of t is equal to inverse Laplace transformation of capital Y of s, which is inverse Laplace transformation of s divided by s square plus 4, right, plus inverse Laplace transformation of 6 divided by s square plus 4, right? I can just apply this, and this is nothing but cos 2t plus 3 times sin 2t, and that is your answer, right? So it's fairly straightforward that using Laplace transformation you can solve, right? Take the equation, apply Laplace transformation on both sides. So the yt solution actually transform into capital Y of s, right? Solve for capital Y of s and apply the inverse Laplace transformation to get the actual value of yt. This is pretty useful sometime, right? When you are solving the equation, just यहाँ से वहाँ ले गए, compute किया value. So basically we are finding the value of Laplace transformation of ft, right, in that s domain, and then from there we will come back using inverse. So as a probably last tea time problem for you actually, right, because today is the last class probably, right? So you can solve y double dash minus 5y prime plus 4y is equal to e raised to power 2t. लाप्लास ट्रांसफॉर्मेशन लगाओगे, ys की वैल्यू लाओगे एंड सो ऑन. ओके, ये मेरा चाय का रहा कप फॉर यू, राइट? ओके, सो नाउ we can also give a formula for Laplace transformation of integral. Laplace transformation of a integral 0 to t f of tau. Laplace transformation 0 to t f of tau d tau is equal to 1 over s Laplace transformation of f of t. T is positive, s is greater than some number alpha, you can say. Okay, so basically, so Laplace transformation of 0 to t f of tau d tau, tau is some, some parameter. So basically Laplace of this is 1 over s Laplace transformation of ft. This is very useful formula, and I think a proof is not very difficult, so I can do it for you. Proof: since d over dt of 0 to t f of tau d tau, what is this value actually? Can anyone tell me what is this value? f of t, correct? तो थोड़ी बहुत कैलकुलस याद है तुमको? So if I call this actually phi of t, this expression, if I call it some function of t, okay, then I can actually use this. So that means Laplace transformation of f of t is nothing but, so actually what I am saying that I am taking Laplace transformation of this equation, okay, on both sides. Then what I am getting is equal to Laplace transformation of phi dash of t, right? Because phi dash of t is ft, right? If this expression is phi of t, so d over dt of phi of t means phi dash of t is ft, right? So I say that it is say, okay. So then this is, now I can apply the formula s times Laplace transformation of phi of t minus phi of 0. Now phi of 0 is 0, so this is nothing but s times Laplace transformation of phi of t. So that means Laplace transformation of phi of t is 1 over s Laplace transformation of f of t. Right, and what is phi of t? This integral, right? So you get the formula, fairly straightforward. Okay, another example. What will happen to the inverse Laplace transformation of 1 over s square plus a? Okay, now you can see that this is something like 1 over s times some function, right? So, if 1 over s square plus a is the Laplace transformation of some function ft, I can find ft, right, by applying some inverse Laplace transform. So basically I can apply this formula to compute this value. So this is nothing but I should say that inverse Laplace transformation of 1 over s times capital F of s will be 0 to t 1 over 3 sine 3 tau d tau, which is 1 over 9 times 1 minus cos 3t. Right. We can just apply the formula. Capital F of s is that expression, right? So Laplace transformation of ft, some f, okay. And of course here I have used this because Laplace transformation of sine 3t divided by 3 is 1 over s square plus 9. Okay, because Laplace transformation of sine θt divided by 3 is 1 over s square plus 9. So a is 9 here, right? So I can just use that fact to compute the value. Yeah, by the way, this is 9, right? I mean, don't be confused. This is 9, right? So this is a simple application. Now another very interesting formula is shifting formula. Very useful. Many times people use it for computing. What is shifting formula? Okay. So suppose Laplace transformation of f of t is capital F of s, right? Then Laplace transformation of e raised to power at ft is capital F of s minus a. Okay, and hence basically f of t is nothing but e raised to power minus at times inverse Laplace transformation of capital F of s minus a. Okay, so I think I am not going to prove it. Probably again I'll say that this is for your cup of coffee this time, right? Okay, so मुश्किल तो नहीं है, right? You just apply. Okay. Actually, why that will come? It's very easy because when you compute, Laplace transformation of this quantity. Anyway, that's up to you. How do you find out? But that's the result. Okay. So now I think there are two important functions which you will encounter in the engineering quite often. Have you heard of impulse function? सुना? अरे मान लो ये बैठा हुआ है, एक मैंने चपाट लगाया तो क्या होगा? So, कुछ impulse आएगा ना? So basically those kind of functions are there. I mean, let me show you some beautiful things. Before that, actually, there is a side unit step function. Unit step function is defined as h of t. So we call it unit step function is 0 if t is negative and 1 if t is non-negative. ग्राफ कैसा होगा इसका? 0 से इधर 0 ही है, राइट? और एक छोटी सी 1 यूनिट का जो है ना एक स्टेप होगा और फिर वो 1 ही रहेगा थ्रू आउट, राइट? फ्रॉम स्टार्टिंग फ्रॉम 0, राइट? आई होप ये ग्राफ को तुम प्लॉट कर लोगे. So we denote, there is some notation, h of t minus a, we call it also ut minus, we define it as ut minus a, or we also define it as uat as 0 if t is less than a, 1 if t is. So what does that mean? अभी स्केल कर दिया, पॉइंट a कर दिया, राइट? आर्बिट्री, राइट? सो a को 0 कर देंगे तो ऊपर वाला फंक्शन आ जाएगा, राइट? पॉइंट a के ऊपर से इससे पहले सब 0 है, a से यूनिट स्टेप है, राइट? थ्रू आउट से यूनिट स्टेप, राइट? फेयरली स्ट्रेट फॉरवर्ड. तो ये नोटेशंस यूज होते हैं वेरी कॉमन, UAT और U of t minus a और HT minus a, राइट? ओके. Now, beautiful formula that Laplace transformation of f of t minus a uat is e raised to power minus as f of s. Right. So obviously, what you need to do in order to compute, you need to divide into two intervals, right? When t is less than a and when t is greater than or equal to a, right? And then you apply the, take the Laplace transformation. Two parts में आ जाएंगे function की value, right? And you can compute and see. Again, I am not doing the proof. And another property. So Laplace transformation of UAT e raised to power minus as divided by s. So that means inverse Laplace transformation of e raised to power minus as times f of s is f of t minus a u of at. All these formulas are quite useful, right? So this is all about unit step function and how we can take the Laplace transform and so on and so forth, right? These are the formulas. Next is Dirac delta function. So there are different forms. I am going to first define what is known as delta sequences. Suppose there is a function omega k of x which is k by 2 whenever mod x is less than 1 by k, means when minus 1 by k, x lies between minus 1 by k and 1 by k, then the value is k by 2 and otherwise its value is 0. Suppose we define this function, then you can easily see that minus infinity to plus infinity omega k of x dx is minus 1 by k, 1 by k, k by 2 dx is equal to 1. So essentially using these sequences you can define this function. These are part of what is known as distributed functions. They are very useful in analysis. There's whole books. I think probably if I remember it, बहुत टाइम से मैंने यूज़ नहीं किया है, but जब पहली बार मैंने पुस्तक पढ़ी थी, I am girlfriend distributed functions, a nice book, depth, there is a lot of depth there. So I am saying that they are very useful also, right? So if you are very much excited, you can look at those books. Books तो पढ़ते नहीं हो वैसे by the way, but right, मेरा काम है बताना, right? So I am telling you that. So these are very useful functions. So let me show you some thing about this function. So this is one representation. So another representation. So I am defining these delta sequences. Second one, suppose second representation omega k of x is equal to k divided by pi 1 plus k square x square, k is positive. Then also you can see that minus infinity to plus infinity omega k of x dx is equal to k by pi minus infinity to plus infinity dx divided by 1 plus k square x square. This value is 1. And I think ये इसको आप complex भी कर सकते हो if you want, right? It's a sort of thing, but this value is 1. Okay. So these are two helping sequence functions. So then Dirac delta function delta x is limit as k tends towards infinity of omega kx. This is our Dirac delta function. Beautiful function. I love this function. Okay. So what could happen actually? You see, if you look at this, say for example omega k of x is k by 2. When you take k approaches towards infinity, what will happen? What will happen to this interval? 1 by k or minus 1 by k, right? So shoot करेगा एक तरफ, right? Origin की तरफ, right? X. और ये shoot होते ही क्या हो रहा है? k by 2 की वैल्यू क्या होगी? Infinity. तो origin पे huge, you know, you can go infinite kind of. जैसे यहाँ पे आप लोगों ने वो देखा होगा, I don't know whether you वाटर शो देखा है ना इधर, स्वामी नारायण मंदिर में होता है ना इधर, अक्षरधाम में, राइट? शायद वाटर शूट करता है ना, इट्स लाइक दैट, ठक से एट वन पॉइंट ओनली, बाकी सब जगह जीरो है, राइट? सो दिस इज द इम्पल्स फंक्शन, राइट? डिराक डेल्टा फंक्शन, ब्यूटीफुल फंक्शन, राइट? So there is some sort of impulse at one point, right? And all other places it is zero. Okay, and such a beautiful thing, this thing remain one, right? So that's something really interesting. Another version is there. So this is what third representation. I would say that suppose delta k of t as 0 for t negative, 1 by k for 0 less than t less than k, and 0 if t is greater than or equal to k. Okay. So now you can see that delta k of t can be written as 1 over k u0 t minus ukt. You can see that why, right? Because u0 t and ukt is defined like this, right? This function u0 t from here. Okay. Or we also write sometime h of t minus h of t minus k, and then delta of t is defined as limit as k tends towards 0 plus delta k of t. So this function is also 0 at so basically 0 everywhere else, and at 0 there is a pulse, right? Infinite impulse, right? Okay. So this is the Dirac delta function. So if we take k tends towards 0 in this expression, okay, take the limit as k tends to 0, what you will get? It's sort of a derivative, right? So basically we will have h dash of t is nothing but delta t. Correct? You see what is happening? H of t minus, we are taking as limit as k tends towards 0, right? So this is sort of a derivative you are computing, right? So we will get h dash of t, and there what will happen actually on the other side? You get delta t, right? Okay, so we will get this expression, right? This is something a very useful result actually. The derivative of unit step function is delta function. Now we should tell you what is known as filtering property. Zero to infinity f of t delta of 0 to infinity, धीरे धीरे लिखो ना, f of t delta of t minus a dt is f of a. अगर कोई भी फंक्शन है उसको हम दिस डेल्टा फंक्शन से मल्टीप्लाई कर दें, विच इज एट टी माइनस ए काइंड ऑफ थिंग, एक्चुअली एफ ऑफ टी की वैल्यू टी इज इक्वल टू ए पे बाहर आ जाती है. ब्यूटीफुल प्रॉपर्टी विच यू कैन वेरीफाई, राइट? Okay, so now keeping these results in mind, Laplace transformation of h dash of t is Laplace transformation of delta t, which is 1. Okay. Similarly, Laplace transformation of t times f of t is minus f dash of s. Okay, derivative with respect to s here. T times ft is this. In fact, a general formula is that Laplace transformation of t raised to power n f of t is minus 1 raised to power n nth derivative with respect to n of capital F of s. This is a better formula. Another formula, Laplace transformation of f of t divided by t. So these formulas are useful when you are computing Laplace and inverse Laplace, right? So we use them quite often. I think all of them can be verified. I am not verifying it for you here, but if you want, you can do this at a cup of tea. If you are still taking tea, right? So s is greater than alpha for some real number alpha, right? Anyway. Yeah, so these are some basic results. One more result I would like to tell you, which is very, very important, known as convolutional theorem. So उसका थोड़ा सा deep meaning है physically also, but actually इस समय इतना समय तो नहीं है physically जाने का, but I can tell you convolutional theorem. Convolution theorem. suppose f of t and g of t are functions defined in 0 to infinity, then convolution of two functions is defined as 0 to t f of tau g of t minus tau d tau, where t is non-negative. This is the convolution of two functions f and g. Okay, 0 to t f of tau g of t minus tau. इसके बहुत सारे मीनिंग है एक्चुअली फिजिकली, बट आई थिंक अभी मैं कुछ टच करने वाला नहीं हूँ. यू कैन लुक एट इट इफ यू वांट. I just want to tell you that Laplace transformation of convolution of two function is Laplace transformation of f of t times Laplace transformation of g of t. So this is nothing but f of s and g of s, product of two functions. This is a beautiful formula. Periodic function का भी था, but अब मैं केवल लास्ट एक एग्जांपल करूंगा. हाउ डू यू सॉल्व पार्शियल डिफरेंशियल इक्वेशन यूजिंग लैप्लास. ओके, partial differential equation, PDE example. So you understand the theorems and results, and then you make the table, and then normally people use table, that's all. Okay, so first of all, Laplace transformation of del u of xt over del x will be what? 0 to infinity del u over del x e raised to power minus st dt, right? That's for the by formula, right? And this is nothing but del over del x, you can take out 0 to infinity e raised to power minus st u of x of t dt, which is nothing but, so now there is only differentiation with respect to x, Laplace transformation of u of xt. So Laplace transformation of del u over del x, where u is a function of x and t, is d over dx of Laplace transformation of u of xt. This formula is straightforward calculation, right? I am using the formula directly. Okay, so now we write, so this is nothing but we write it like d over dx of u of xs. See our convention that small function will become capital function, right? Now this will be function of s only, right? So that's what it is. Okay, so now the last example, there is a partial differential equation we want to solve. So keeping this formula in mind, so suppose equation is del x times del u over del t plus del u over del x is equal to x into t. U of x0 is 0 and u of 0t is t. Initial value problem, I would say again. Okay. So how do you solve this? If we keep this notation that Laplace transformation of u of xt is capital U of xs, right, which is quite obvious, right? If this is the notation, then I can apply Laplace transformation on both the things, and actually I will use this boundary condition this here, right? So we get x times s of u of xs minus u of x0 plus d over dx of u of xs is equal to x divided by s square. Okay, because we are doing with respect to x, right? Sorry, t. So t becomes 1 over s square, right? So now we know that u0 of, now we can do the transformation on these conditions also. So that means we know that u0s will be 1 over s square, right? From here. Okay, I can apply the transformation on both sides. So that means we get, simplify, I can simplify this, right? You will get du over dx plus s times xu is equal to x divided by s square. Do you agree with this? du over dx, that's the first term, s times x times u. वो ब्रैकेट की चीजें मैं नहीं लिख रहा हूँ, ux0 की वैल्यू मैंने 0 डाल दी है, राइट? So we arrive at this. So partial differential equation after transformation becomes ordinary differential equation. Now I can solve it easily, right? And since this is first order equation, I need to find integrating factor. If you remember, integrating factor is e raised to power s times x square by 2. So solution will be e raised to power s times x square by 2. Capital U is equal to integration x divided by s square e raised to power s x square by 2 dx plus some function, some constant which is only function of s. So this is nothing but 1 over s cube e raised to power s x square by 2 plus a of s, right? So this implies that we have the value of u of xs is equal to 1 over s cube plus constant as times e raised to power minus s x square by 2. Now using the condition that u0s is nothing but 1 over s square, I got it. How? By transformation here, right? From this equation if I apply, you can see that here u0s is 1 over t square, sorry 1 over s square. So I can use this value here. We get the value of the constant a of s as 1 over s square minus 1 over s cube, right? Which is only function of s. So uxs becomes 1 over s cube plus 1 over s square minus 1 over s cube e raised to power minus s x square by 2. अभी हमारा आधा काम हुआ है, right? I have to find uxt. So I apply inverse Laplace transform on both sides. Inverse Laplace transform. So, and actually we are going to use shift theorem here, if you remember, because here this product is exponential. If you remember what is shift theorem, again recall. This inverse Laplace transformation of e raised to power minus as f of s is f of t minus a times u of t, u of at, right? I am going to use this formula directly there, right? Inverse Laplace transform of shift formula. So this here I will apply shift formula. So I will get answer as uxt is equal to t square by factorial 2 plus t minus x square by 2 minus half times t minus x square by 2 product by u x square, sorry, u x square by 2 t, okay, and that can be broken into t square by 2 when t is less than x square by 2 and t square by 2 plus t minus x square by 2 minus half times t minus x square by 2 whole square when t is greater than equal to x square by 2. थोड़ा सा calculations है, but otherwise technique is very simple, right? Whether it is ordinary differential equation or partial differential equation, apply the Laplace transformation. When you are applying Laplace transformation, you also apply on the conditions, boundary conditions and so on, and you find the value, right? Go into the, so from t domain equation is converted into s domain where it becomes ordinary differential equation, solve it and apply the inverse Laplace transformation. And all these formulas, shift formula and all these for different functions, you can use it, right, in order to calculate. So तो ये भी खत्म हो गया, अभी क्या बचा? In fact, now something I can give you just towards the conclusion, something really interesting. I think you might have heard about these functions, beta function, gamma function. Someone, young person like you, he went to the library and he was looking at these functions one day about beta gamma function, and he realized that he can do something with these functions. And he came up with this idea of string theory. Have you ever heard of string theory? क्या है string theory? Everything vibrates in terms of string, right? So you can actually describe the universe in terms of strings. Okay. So this, all this is coming from these beautiful functions, right? So someone from you may want to look at, actually there are some videos on YouTube you can find, Elegant Universe. Okay, series of videos are there. So how universe can be described in terms of strings. And in fact you will see there, this person, they are mentioning how the person was, turning the pages and looking at this beta and gamma function and came up with this beautiful idea. And I think you already know that when we wanted to integrate integration of sine of x cube, we came up with incomplete gamma function, right, which is another interesting thing. So I think sine of x cube का इंटीग्रेशन आप अपने साथ रख सकते हो, राइट? कोई बहुत ज़्यादा अपने आप को स्मार्ट समझ रहा हो तो उसको ये दे सकते हो. Can you solve? So you will see that it is, I think it took you about 1 week or so to get the solution, right? So I mean something really interesting. Anyway, so let me show you something about beta gamma function. Euler's beta function. B of x comma y is equal to 0 to 1, t raised to power x minus 1, 1 minus t raised to power y minus 1 dt. Here real part of x is positive, and actually you can define it for the even complex ones also, right? But anyway, I am just talking about so dt actually, right? So this is a beta function. The first property that beta of x comma y is same thing as beta of y comma x. These are known as special functions, right? Then there is a gamma function which is very interesting function. That gamma of z is equal to 0 to infinity t raised to power z minus 1 e raised to power minus t dt. So this is convergent for real part of z positive. Okay, this is gamma function. Now there are some properties. Actually, you can think of gamma function as extension of factorial function. Factorial function you saw, right? Factorial n is equal to n into n minus 1 into n minus 2, right? Dot dot dot, right? So it's kind of generalization here, right? So basically, if n is positive, and of course I am talking about integers, positive integers, then gamma of n is equal to factorial n minus 1. That's first formula you can find. So each of these formulas you can, okay, you know what to do with this. Third, gamma of z plus 1 is equal to z times gamma of z. Integration में रखोगे directly z बाहर आ जाएगा. You can see that, right? Formula. You can verify. Fourth, gamma of 1 is 0 to infinity e raised to power minus t dt is equal to 1. Okay. There are some alternative definition of gamma function. Limit n tends to infinity, factorial n divided times n raised to power z divided by z, z plus 1, z plus n. That's another formula. Z plus 1, z plus 2 up to z plus n. Okay. इन सब का प्रूफ चाहिए होगा. प्रूफ तो अभी नहीं है हमारे पास, बट this is another very interesting result. What is this gamma? Small gamma, do you know? Euler constant or Euler-Masonry constant, I don't know whether you know about. Okay, that's very interesting function anyway. You can also prove the following property, that gamma of 1 minus z into gamma of z is equal to pi times sine pi z. 6 gamma of half is equal to square root of pi. ये सारी फॉर्मूले निकाल सकते हो from that integration, right? And one very interesting result which I am not going to prove. Proof इसका दिया हुआ है, simple integration है. You can look it into the notes. Gamma x into gamma of y divided by gamma of x plus y. Beta और gamma function का connection. Beta of x comma y is gamma of x into gamma of y divided by gamma of x plus y. I mean, you can actually compute these two things, take a product, there will be double integral, do some substitutions and calculations, you will arrive at the answer, right? So another interesting thing that beta of mn is 0 to infinity x raised to power m minus 1 divided by 1 plus x raised to power m plus n dx. Okay, that's another representation. By the way, ये सारे functions रामानुजन को तो ऐसे ही दिखते थे, right? So he's written a lot of equations like this. So you can also, पर उसके लिए आपको जो है ना थोड़ा सा ध्यान लगाना पड़ेगा. So I have visited Ramanujan's birthplace. There is a temple also, Namakali Devi temple. Have you seen that in Tamil Nadu? So it's a beautiful place where he used to do all these calculations, right? And people used to ask him, how do you get these formulas? So he said it's all the Devi's Krapa, right? Namakali Devi has given him all these formulas. So something this is really interesting. Some of them are there. Anyway, so I think that's all about whole thing. There are certain differential equations like Legendre equation, Bessel equation, which can be solved using series solution. Since I have skipped that part, I am not discussing this anymore. But those are the solutions of those differential equations are also known as special functions. And these functions have a lot of applications, which anyway we are not touching. So I think we are in time and we have done with whatever we can do with the calculus, right? So thank you very much. Hopefully some of you will get double A, right? Because you can get full marks anyway in the final, because differential equation is very easy thing, right? So syllabus आज तक का course है, right? I hope section B में भी यहाँ तक cover हो जाएगा, so we can announce in a day or two, right? What will be the syllabus? Of course, after second midsem, right? So there is not much to do. So I think after this we are not going to take any further class. It's all done, right? You have enough time to prepare. Okay. So read. I mean, you should read a lot, right? Try to read as much as possible. And I think some of the projects I was looking at it, I will see. As I mentioned, I have sent the entire Excel sheet to all the faculties and get their feedback. इतना सारा काम कैसे करेंगे ना, सबको distribute कर दो. So basically, so let us see who can give us best project, right? And I will share that information with you, right? So anyway, I will also look at it. Finally, I have to grade anyway. So that's all. Thank you very much, and hopefully see you sometime in next semesters. Okay.